All right, we are going to now move on to chapter 4, which describes the relationship that we have between two variables. So we are going to be graphing two variable data and learning how we do that here. So the first section we're going to work with is going to be how do we draw the graph for them. Next, learning about the correlation coefficient. So what is it? And then how do we compute it? And then finally for this section is what is the difference between a correlation and a causation? So there are two different types of terms. All right, so the first thing we're going to do is we are going to look at what these variables are called. So we have two variables, x and y. So the response variable is the variable whose value can be explained by the value of the explanatory or predictor variable. All right, so explanatory is the x variable. It is also a predictor variable. It determines the outcome. So this is also called the independent variable. All right, so x variable, also explanatory, also predictor, also independent, can determine the y variable, the response variable, also known as the dependent variable. Okay, and the graph that we are going to use to graph this data is called a scatter diagram. It is a graph that shows the relationship between two quantitative variables measured on the same individual. So each piece of data is paired. The way we're going to do that is the x is on the horizontal axis here, and the y is on the vertical axis. So if you've taken algebra anytime recently, we know that our coordinate plane always has the x on the horizontal and the y on the vertical, and we are going to continue to follow that here. All right, so how do we draw a scatter diagram? Again, we always start with the kind of by hand method, and then we move to the stat crunch method. At the end of the section, I'm going to do an example fully with the technology, but I'm going to show you now how we do by hand. So right now we have the relationship between club head speed of a golf club measured in miles per hour and the distance in yards that the ball travels. So the club head is the x speed, club head speed is the x, and the distance traveled is y. Because depending on how fast that club is traveling, how fast I hit the golf ball is going to determine how far my ball goes. Okay, default follow that the x variable is in this first column here, and the y variable is going to be in your second column here. Okay, I will give it to you that way. So x is the first, or the independent, y is the second, or the dependent. All right, so the way this is going to work is these are paired pieces of data. 100 goes with 257. So on the axis here, I'm going to find 100 on the x, go up to 257, and I'm going to put a point there. And then I'm going to repeat that for every single pair of values. So 102 and 262 is right here, 102, 262. I repeat that for all the data values, and the end result here is called a scatter plot. And you can see here that it does follow kind of what I mentioned at the beginning, that it would make sense that as my club head speed increases, as it gets faster here, my ball travels further. Okay, if I hit it at 105, the ball went further than if I hit it at a speed of 99. It didn't go as far. Okay. Logically, that makes sense. Okay, sometimes though you don't, like I said, it's not clear which variable should be your x and your y. Again, I'm always going to follow that general idea that x is your first variable and y is your second variable. That's how I'm always going to give you the data. Okay. Just know that scatter diagrams will show any type of relationship that exists or doesn't exist between two variables. What we are working with here are linear. There are other relationships called nonlinear relationships, which we will look at here in just a little bit. There's also ones that have absolutely no relationship whatsoever. Okay, they just don't happen. There's nothing I can do to make them have a relationship. All right, so let's take a look here at some examples. All right, so this first example here is explanatory linear. There's an explanation here, and it is linear. Okay, I follow or draw a line between all my points here that generally follows the direction. All right, same here. This line, except it's going in a different direction, but all these points generally follow this line here. Okay, next one here, there's an explanation here. All these points follow the same kind of pattern here, but it's not linear. Okay, this is not a straight line. This is a curve. Similar to this one, these data follow a pattern, but it is not a line. It again is a curved line. Okay, we are not going to work with these. These are not ones that we're going to work with. We're only going to work with these linear ones. But sometimes you may come across something like this last one, where however you graph the data, there is no relationship here. It doesn't make any sense. I can't draw a line up this way. I can't draw a line down. There's no relationship. It doesn't work. Okay. So like I said, the ones we're going to work with are really these two. We may come across something like this, but the other ones we're not going to work with. So we're going to talk about this first one here. This example A here is what we call positively associated. And this first line here makes it really kind of weird to understand. So I'm going to go to this bottom line here, and that's what the definition really makes a little more sense. Okay, so that is, they're trying to clarify this really wordy part up here. Two variables are positively associated if whenever the value of one variable increases, the value of the other variable also increases. Okay, so let's look at this. And we always look from left to right. What you're going to do is look from left to right. How do the points move? Okay, well, in a positive association from left to right, they are going to move up. Okay, here's why. This is a number line that as I move this way, they are getting larger. And as I move up this way, these values are getting larger. So from here to here, I have gone positive increased and positive increase. There are two positives. They are the same sign. So when I have the same thing happening in both variables, increase, increase, I have a positive relationship. In a negative relationship, we're going to have when one increases, the other decreases. So what's going to happen now when I go from left to right is one goes up and one goes down. Okay, so from left to right, the points are going to go like this. So as I go this way, these values are going up. But as I move this way, the points are falling down. As I increase to the right, my points are falling down. Those are opposites. One goes up, the other comes down. It is a negative relationship. Okay, this negative and this positive relationship back here are going to transfer over into both our slope and our correlation coefficients. Okay, which is what we're going to talk about next here. So what is a correlation coefficient? A correlation coefficient is the measure of both the strength and direction of a linear relationship. Okay? This only measures a linear relationship. So if my data does not follow a line, it's going to give me a value for a correlation coefficient that tells me it's not aligned. And just like every other done so far, we have Greek values for our population and regular variables for our sample. Okay, so I'm going to go back here and review a little bit with you. U was the mean of the population. Sigma was the standard deviation of the population. And now this Greek letter rho is the correlation coefficient of the population. So anytime you have a Greek symbol, you are talking about a population value. Versus a sample, we had X bar for the mean, we had S for the standard deviation, and we have R for correlation coefficient. I am going to show you the process eventually here. But before we do that, we're going to look at what the correlation coefficient tells us and the nasty formula. All right, again, here's why we don't do these by hand. There are so many variables. 1, 2, 3, 4, 5, 6, 7 variables that are in here. We've got our data values, our X mean, our X standard deviation, our Y data values, our Y mean, our Y standard deviation, and how many pairs of data I have. Okay, it's a lot of math. This is one version of the formula. I'll show you an even scarier version of the formula here. So they're not fun, okay? I will, again, like I said, show you one example. So if you want to see how to do it or you want to understand it, fine. But I really want you guys to focus on using StatCrunch because that's what it's here for. It's here to save you guys the time. I want you to be able to get the correct answer so you can tell me what does it mean. I don't want you wasting 20 minutes calculating it, okay? Type it in, give it, 10 seconds, and it spits out the answer. I'm still talking about this correlation coefficient here. A linear correlation coefficient is always going to be between -1 and 1 inclusive. So that means it can be -1, it can be +1, it can be anything in between there. Okay, if R, or the correlation coefficient, is exactly +1, we have a perfect positive linear relationship. Okay, 2 terms there, strength and direction. If R is -1, we have a perfect negative linear relationship. If R is closer to +1, the stronger it is going to be. So the closer I am to 0.1, if I'm at to 1, 0.9, 0.8, those are still very strong values. Further away I get from 1 and closer to 0, which we'll see on the next slide, the weaker we're going to be. Okay, the same happens with the negative side. The closer you are to -1, so -0.9, -0.85, stronger you're going to be in the negative side. If R is close to 0, then we have little or no evidence of a linear relationship. Okay, it doesn't mean that there is no relationship at all. It just means we cannot do a linear relationship. It could be a curved relationship. There is no unit that is attached to this. It's just a number that tells us how strong and the direction of our relationship. Okay, and the last thing is that it is not resistant. So if we have kind of like an outlier, or we have points that seem to be far away from the other values or don't seem to be following the trend of the data, it is going to impact my correlation coefficient. Okay, it's going to tell me it's not as strong as it could be if that point wasn't there. Here's where it makes a little bit more sense because we're actually looking at a visual to see what's happening. All right, so first example here is that you're going to get an R of 1, okay? No matter what I do, draw my line here, I'm hitting every point exactly. perfectly. That is a perfect positive. Positive because it is going up from left to right. B, we still have a really strong positive. I'm still moving in that positive direction here, but you'll see a little bit of variation from the line. They're a little above, a little below, but still really close. Okay, so this one has an R value of about 0.9. It's still very strong and it's still positive, but it's not perfect anymore. Okay, and as I move here to C, you'll see that the points are getting even further apart. Okay, I still generally follow that positive direction here, but there's a lot more down, a lot more up, a lot more points just kind of all over the place. All right, and so this one's called, the book refers to this one as moderate positive and an R of 0.4. Usually, I think moderate kind of cuts off at about 0.5. That was kind of how I was taught. But depending on where you look, it's a little objective or subjective, right? Where you look, there's a little bit of a kind of opinion involved there. So a lot of times I'll still consider strong about like, it kind of depends, usually around like 0.7 or so. And then about 0.5, anything below 0.5, I usually consider weak. Okay, same thing can happen in the negative direction. So we can have a perfect negative where all the points follow on the line, but negative. All the points are really close to the line, still negative. So you can see here, this is just the opposite negative version. This is a moderate, or you could say weak. It depends on how you look at it or how far apart these pieces actually are. So it's a little subjective what you think. But the biggest thing is when you get that R value, you're going to tell me those two things. What's the strength and what's the direction? Okay, when I look at this, there is no way to draw a line. It doesn't follow, no line. So my R value is going to be close to 0. If it's not 0, it's going to be really close to 0. The same thing can happen here. This is not a line, it is a curve relationship. So again, the R, or the linear correlation coefficient, is going to be close to 0. There's no way to draw a line through that data. Let me show you how we would do this by hand. So those of you that like to see this, you can see it. If you are not a person who wants to see this, you're going to skip forward. Let's see, 1, 2, 3, 4 slides. Just see how to do it with technology. All right, so here's our data. 5 pairs of data here, 118, 313, 39, 66, 74. So I got my data. So what you have to do here is you would first plug your data in to most likely StatCrunch. X would get its own column, Y would get its own column. And you would find the average of X's is 4. The standard deviation of the X's is this. The mean of the Y's and the standard deviations of the Y's. The next step is to take every single data value minus the mean divided by the standard deviation. Okay, for all the X's and for all the Y's. That's what they're doing here. They're taking 1 minus 4 divided by standard deviation. 3 minus 4 divided by standard deviation. 3 minus 4 divided by standard deviation. So on and so forth, all the way down here. Then I do the Y's, take 18 minus its mean, 10, divided by the standard deviation. 13 minus 10 divided by standard deviation. All the way down here. Okay, some are going to be positive, some are going to be negative. Okay, next step would be you multiply this one times this one, get your answer. Multiply over here, all the way through. And then finally, you are going to add those up. But we're technically not done. So it's not really finally. There is one step after that. And that last step is to take that answer we got divided by your degrees of freedom. So remember that degrees of freedom, how many we had, take away 1. So there were 5 pairs of data, take away 1. So I'm going to divide that by 4. And what I have here is a very strong negative relationship, okay? It is negative and it is 0.94. That is very close to 1. It is a very strong negative relationship. And it makes sense here. It looks like I could draw a really good, sorry guys, a really good straight line if I can draw here. There we go. Almost looks like those 4 could all fit on a line, and maybe this one guy here would be off. Looks like it. All right, so lots involved. So what we're going to do instead is we're going to do this in StatCrunch. All right. So it was club speed and distance. Okay, they were 100, 102, 103, 101, 105, 100, 99, and 105. And the distances were 257, 264, 274, 266, 277, 263, 258, and 275. So the way that we are going to do these in StatCrunch here, stats, regression, and we are doing linear. Okay, we are selecting our x to be our first variable club speed, y to be our distance, and then you don't need to click anything else, just click compute. Okay, what's going to pop up here is we're going to get 2 different things that happen. It's 2 pages. It says 1 of 2. So this first page has some extra stuff on it, which we will talk about in the next section here. But right now it's just asking, hey, what's our correlation coefficient? So 0.93869, 0.9. It's strong and it's a positive. So this is a positive, strong relationship. Now, if I want to see the scatter plot, I go over here. And it's going to have all my points graphed and my trend line right down the middle to kind of show you how my data is falling. All right, so let's look at another example here. Go to my slideshow. And you can see here, same graph, same correlation coefficient is a positive, strong relationship. All right, so here's another one here. Graph the data and explain the linear correlation. So you guys can click open the data sets. So you have our credit score and interest rates. So it looks like here as my credit score goes up, my interest rate is going down. So I should automatically know that this is a negative relationship. So stat, regression, simple linear. X is my credit score and Y is my interest. Okay, so even if you didn't know, the first one I gave you is credit score, the second one I gave you is interest, X and Y. All right, so we said, hey, that's an inverse or opposite relationship here. Sorry, as one goes up, the other goes down. My correlation coefficient should be negative. We've got negative 0.975. Again, very strong negative relationship here. And I should, if I go to my graph, see that my points here are pretty close together along that line. So there's one other little thing we have to discuss in this section. But I hope that makes sense so far of just how you get to calculate that correlation coefficient. So the last thing we have here is what's called a lurking variable and causation correlation. All right. If data is observational, we cannot conclude that they have a causal relationship. We cannot claim that one causes the other to occur. Okay, we are only looking at observational data. there can be things called a lurking variable or some other influence or variable that can impact why this is happening. So the only way that you can ever, say one thing causes the other to happen is if you are doing a full-on experiment, placebos, all of that kind of stuff. Here's an example. For example, as air conditioning bills increase, so does crime. Does that mean that folks should turn off their air conditioners so that crime rate decreases? No. Okay. It's not that air conditioning causes crime. There's no relationship there. There's no, causal relationship there. It is true that in the summer months, when it is warmer outside, crime happens more frequently. Okay, so the air temperature outside is having an impact on how much we use our air conditioner, and it's also impacting the amount of crime. Okay, but it is not, I cannot say that, well, when I increase my air conditioning, it is going to cause the crime rate to increase. Okay, you can't claim a cause. You can just claim that, hey, there's a relationship here. When my air conditioning increases, there's been more crime. Okay, so I'm going to look at another example here. This is a study that was done on the number of colas per week that 15 different women drank and their bone mineral density. So she wanted to just look at how many Cokes do you drink and what's your bone mineral density? Is there some sort of relationship here that if I drink more Coke, something happens to my bones, especially in women? This is a prospective cohort study. So right there, this is observation. Okay, all I can claim is a relationship. I cannot claim that one causes the other. So let's take a look. The figure on the next slide is going to show us our scatter diagram, and it's going to tell us that, yes, we have a linear relationship here. But it does look like if I drink more colas, my bone density goes down. Okay, it looks like that. Okay, but again, because this is observational, and the authors conclude that an increase in the number of colas consumed causes bone density to decrease. And the answer is no, because it is observational. So what they want you to do is they want you to say, okay, well, what are some other variables that could impact this? What could cause a woman to have lower bone mineral density besides just how much soda she drinks? So here, it's observational. So we cannot claim a cause. Here's some other options. Age, your body mass index, your height. Were you a smoker? Drink alcohol? How much calcium do you take? Do you drink caffeine? And how much physical activity you do? Do you use any hormone replacement? Where are you in your menopause? There's so many other things that could impact bone mineral density, genetics, that we can say, okay, there's clearly a relationship here, but I can't say that one causes the other to happen. So we just have to be really careful in our wording when we talk about these relationships, because they're relationships. There's relationships, correlation, but I can't say one causes the other. Okay, so just know that the authors were careful to say that increased cola consumption is associated with lower bone mineral density, but they never once stated it causes it. So just things to note, to look at when you're, reading, or if you're ever gonna write any form of statistic stuff here, that when we're talking about these relationships, one can relate, but very rarely, unless we're working with a true designed experiment, can we ever say that one variable causes the other to occur. Okay, so there you go. Linear correlation coefficient. What does it mean to be a correlation versus a causation, and how you graph those scatter plots. All right, see you in the next video.